and way too unruly to look up. And the solution was to come up with the idea that what we should list is the standard enthalpy of formation. What does it mean to form something? Yeah, sandcastle. Hey, if you want to make a sandcastle, what do you need? A bucket, sand, and some water, right? Because dry sand isn't going to make a castle. If you want to make a sandcastle, you need all the parts that make up a sandcastle. If I said I made a sandcastle, your assumption would be that I started with sand and water in a bucket, right? Not that I started with some really more complicated, bigger sandcastle and I like whittled and carved it down to make a smaller one. That'd be a weird way to make a sandcastle. Right? You'll find some other kids and like
that's actually the smart way. Why don't people do that?
I don't think it is the smart way. So when we make a database of enthalpies of formation, what we say is, okay, let's imagine any chemical you can imagine. What would the enthalpy change be just to make that chemical? That makes sense. And when we say make it, we mean make it from its most basic parts. So let's look at an example. This is table 5.3. So titled because I shamelessly stole it from a Google image search. I couldn't cite it if I wanted to. It was just the top hit, and I dragged it into my document. But if we look here, it's got acetylene, all right? C2H2, which is a gas. And it has its delta H naught F, which is how we read this. Delta H naught F. And we know what most of these letters mean. We know that delta H means change in enthalpy. Yeah, not heat would be at least mostly true because we assume that enthalpy change gets released or comes from heat. Temperature, not correct, but good. The naught, this little symbol up here, all right, just means standard temperature and pressure. So something we're not going to get into in this course, but something to be aware of, is that all of these numbers change if you change atmospheric conditions. So if you did this reaction in hotter conditions, the numbers would be a little bit different. If you did them under colder conditions, they'd be a little bit different. If you did them under high pressure, the numbers are a bit different. If you do them under low pressure, the numbers are a bit different. We're not going to get into that. So we use this little symbol, which is called naught, to say that these numbers are done under standard laboratory conditions, which is 0 degrees Celsius, 1 atmosphere of pressure. In SI units, 101.3 kilopascals. And what's 0 Celsius in Kelvin? 273.15 Kelvin. So this assumes 273.15 Kelvin and 101.3 kilopascals is the conditions under which these are done. It just means if you're a chemist and you're trying to do things standardly, this is what you would set the laboratory conditions up for when you did the reaction. Yes, sir. Those numbers, they will come up because I will definitely give you questions at some point where you have to use PV equals nRT. And so when I give you a question where you have to use PV equals nRT, the nice thing is you'll know the P for pressure and you'll know the T for temperature. Because the P for pressure will be 273.15, oh, sorry. The P for pressure will be 101.3 kilopascals, and the T for temperature will be 273.15 Kelvin. Don't worry, I will remind you of that, those specific numbers. It is not important to me that you have them memorized, though you will, because it just happens. And then lastly, F stands for, what do you think? Formation. So when we talk about a compound's delta H naught F, we're saying what is the change in enthalpy if, under normal lab conditions, I make a mole of this stuff. Does that make sense? How much heat would be released or how much heat would be absorbed if in the lab, under normal conditions, I made 1 mole of this thing from its elemental components. That make sense? from the elements it's made of. So let's just look at this first example from the textbook. Well, from the, I haven't given you a textbook, so from the scanned page on Google. Yeah. We are trying to make C2H2. What did we make it from? It's only made of two things. Yeah, carbon. And when I put hydrogen, what do I need to remember? Yeah, hydrogen's a diatomic gas, so it'll be H2. We are always just going to make these things from their elements. By the way, you're never going to have to make equations like this for it. I'm just showing you what the idea is. So for every one of these, we could say this is just made of carbon, which is typically a solid, and hydrogen gas. And you always use the most common elemental form of that thing. Does that make sense? So carbon in its most common form is a solid. So we would use solid carbon. Hydrogen in its most common form and at these temperatures, remember, is a gas, and it's H2. And is this balanced? How would I balance it? There we go. So that would be the formation reaction. Again, after today's lesson, you're never going to draw one of these again. But just to show you, if I'm a chemist and I want to figure out the delta H naught F of a reaction, so I can post it in the textbook, this is what I'm talking about. I'm talking about what would the delta H be if we made the thing out of the elements it's made of. In this case, C2H2 is made of carbon and hydrogen. So I'm going to react carbon and hydrogen and then this balance. Does that make sense? Questions about that? Okay. What would the delta H of this be now? Look at the chart below. For this reaction, the delta H would be 226.7 kilojoules. Yeah, and again, when we report it as a delta H naught F, yeah, we have to say per mole. When I'm putting it next to this equation, how much of this have I made? 1 mole. So it's just 226.7 kilojoules. Does that make sense? Though, yeah. We could then say, therefore, the delta H naught F of C2H2 is 226.7 kilojoules per mole. Again, this work isn't the important part. I'm just showing you where this comes from. Does that make sense? Point being, for any compound you can imagine, its delta H naught F can be found and reported. And keep in mind that it's just going to be the reaction that made it out of its elemental parts. On a side note, what is the delta H naught F? What's the formation enthalpy of carbon, or O2, or H2, or iron? Any of these things. Well, remember, we said these are the reactions when you make these things out of their basic pieces, right? So, do you have to do a reaction to make carbon out of its basic pieces? No, it's already its basic pieces. Do you have to do a reaction to make oxygen out of oxygen in its most common form? No, it's already itself. So what would you guess the delta H naught F for all of these things is? 0. Good. So when you go to use this, it doesn't take any energy to make these things from the starting points because they are the starting points. That's going to come up when we go to use this. Now, I've given you a small table here with some common stuff. When you get your assignment package, it may not be on here. If you don't have the delta H naught F for something, what should you do? Search for it. On any Wikipedia page for common compounds, it will list its enthalpy of formation. It's like there's a million resources. It's a very common chemical characteristic that we write about. So if I give you a question that involves something we don't have on here, that's fine. If we had a textbook, there'd be a big 3-page chart at the back of the textbook that you could look them up in. But like honestly, it's a good thing to be able to look that up and find it. Okay, so let's introduce delta H naught F to our buddy Hess. Remember that Hess tells us what? What does Hess tell us about a reaction? That we can take a bunch of different reactions and we can algebraically manipulate them to give us a new reaction. Good. So let's imagine this. And this is going to be ugly, and we're only going to do it once. Okay? So what we're about to do is messy. We're only ever going to do this messy thing once, because once we're done with that, we're going to look at it, and it's going to tell us what we need to know, and it'll give us the shortcut at the end. So this is a long-form version of something that's going to teach us a shortcut that's real quick. Okay? Do you have faith in me that if we do something that takes 15 minutes and is a little confusing, but at the end you're going to go, I get it, and here's this nice, easy, shiny thing I can do that takes like 5 seconds for any reaction?
It's like you think somebody has to do it.
That's right. First time's tough, and then after that, it's nice and easy. So just please, please, please have faith in me, and I have faith in you. Okay, we have here a reaction that we want to model. Does that make sense? Okay. We want to figure out the delta H of this reaction, and we don't know it. And all we have to work with is the table I gave you on the previous page. What we're going to do is use enthalpies of formation to do it. Okay? So let's keep in mind how many things in here will have an enthalpy of formation. Will C3H8? Yeah, it's made of carbon and hydrogen, right? Going to have a reaction. Okay. Does O2 have a delta H naught F? No, because it's already elemental, right? You can't, it's not made of anything simpler. Oxygen gas is the simplest form of oxygen. What about carbon dioxide? Yeah, it's made of carbon and oxygen, right? What about water? Yeah, it's made of hydrogen and oxygen. So how many reactions are we going to have to combine to get this? 3. Okay, so let's take a minute and do that. So our first reaction is going to be the formation of C3H8. Well, we always make these by just combining what? The basic elements. So we're going to have carbon reacting with hydrogen to make C3H8. Okay. Hey, what is needed to balance this? And? Cool. Now, the delta H for this, we can just look up, right? And it should be on the previous page. So is C3H8 on there? Hopefully I didn't screw up. I see it. By the way, what's C3H8 called?
Propane.
Propane. So what's its delta H naught F?
Negative 103.85.
Okay, so negative 103.85. There you go. Okay, what's the next one we're going to do?
Carbon dioxide.
Okay, we're doing carbon dioxide next. And what's its formation going to be? Well, what's it made out of? Carbon and oxygen. And what's that going to give me? Obviously, it's going to give me CO2, but what's it going to give me in terms of enthalpy changes? Previous page.
Negative 393.
Negative 393.5 kilojoules. Good. Okay, good. Because somebody has taken the time to sit down and do that reaction and figure out how much energy it takes. That's how much energy it takes. What's the third thing we need to worry about here? Water. Okay. Yep.
For the CO2, don't you do the CO2?
We'll get to that. That's going to be, you're totally right. You're just jumping ahead. First, we're just going to figure out what these reactions are. Then, yeah, we're going to make them work for this actual equation. All right. And our third one is going to be making water. What do we make water out of? Good. And we said O2 is the one place in life where we are allowed when we need to do what? Yeah, we can use a fraction. If you wanted to balance this out as 2H2O, that'd be fine. But then you'd have to remember to double the delta H naught. So we're just going to say it takes half of an oxygen. Is everyone comfortable with that? Tell me if you're not. Again, it's just allowed because otherwise it makes balancing all kinds of equations miserable if you always are doubling things to make oxygen work and hydrogen. And the delta H naught F for this is what? It's going to be negative because we're burning something.
Negative 25.8. Oh, wait, no. We're dealing with water vapor, so it's going to get 241.8 because it's gas formation.
Oh, but you know what? I misspoke or I miswrote, but it's looking for the liquid formation, right? Because our equation looks for liquid. So it is 285.8? Yes. Sorry, Alondra, that's on me. I put gas down here, but we can see from the equation it's liquid water, which let's say I was just testing you to make sure that's a lie. That's a lie. Okay, now let's just do Hess's law. And hey, everything's pre-highlighted, which is kind of nice. There's our water. There's our carbon dioxide. And there is our propane. So let's ask ourselves, to do Hess's law on this, over here we want propane on the left. Here it's on the right. What do I need to do with this first equation? I need to reverse it. Anything else? Is the number in front of it good? Yeah. Cool. Okay, so that one's done. Let's look at the second one. Here CO2 is on the right. Down here it's on. So I don't need to reverse it. Am I good?
No.
What do I need to do? Very good. So we're going to do 3 times this reaction. Right? Because I need 3 of them. All right. And then the last one. Here water is on the right. Down here water is on the right. Am I good? I need to do 4 times it. Good. Does that make sense? Again, the nice thing, you're never going to do this again. But it's not that difficult, is it? It's just annoying. So now let's do this. What am I doing on the first one? Reversing it. So can somebody I haven't talked to in a while tell me what I'm going to write here? Somebody feeling bold and brave and brave and bold.
Wait, are we putting this in the section 2 or section 1?
No. I mean, maybe. No, we're good. They're both giving me, signs of life. Anybody? Worst case scenario, you're wrong. I'm wrong like 11 times a day. Let's go. Yep. Fantastic. And what's my delta H on that? Very good. Okay, next reaction. I don't know why I went so far to the right with that. That seems silly.
So if we also went too far to the right, just move it over.
Yeah, just slide it on over.
Use the button on here.
Yeah, don't forget to use the button. Otherwise, it just draws around it, and that's embarrassing. Okay, so our delta H is now positive because we've reversed this guy. Very good. That takes care of 1 for us. Somebody else, feeling bold. Give me number 2. Yeah, Kevin, what you got?
I got 3C solid.
Yep.
Plus 3O2 gas
yields 3 CO2 gas.
Great. And I'll give you, it'll probably take you a moment, I'm sure, but when you have it, you can give me the delta H.
So it's negative 1,180.
1,180.5.
Yes.
Fantastic. Thank you. Anyone with questions about that? Does that feel good? That makes sense? All right. And quattro. I mean what I meant. And I'm pretty sure it says 3 and always said 3. There are 4 lights. 4 lights. Quiet. Yeah.
Why did you switch from delta H not F to delta H?
Because it is no longer the delta H not F, right? Because delta H not F specifically refers to 1 mole of this stuff in the forward direction, and that's not what we're doing now, right? So this number here is -1 times delta H not F. So it's not delta H not F. This is 3 times delta H not F. So it's not delta H not F. Does that make sense? Not a big deal, but if we're being pedantic, it isn't the enthalpy of formation of 1 mole of that thing anymore. We're now talking about having manipulated it. And that's a good question, by the way. It's a semantic point, but it matters. Okay, the third one. Not the fourth one. Who would say that? Yes. Yeah. Wait, and if I can just pause, everyone's comfortable with the fact that we end up with 2 oxygens because 4 times a half is 2. That's comfortable. Cool. Gives me what? Cool. And my delta H for that is what? Cool. And now, if we've done this right, if it all works, we should be happy campers. So let's see what happens. What cancels? Okay, so 3C cancels with 3C. Gone. What else cancels? Okay, anything else? All right, so what's the sum total of my reaction? Yeah. Great. And so this has been carried up in some strange circumstances where the liquid is allowed to condense immediately. Probably I meant to write gas when I made the question, but whatever, I didn't. And what would the delta H of this thing be? Going to be on the order of like -22 something, 22, 23.7? Oh, I forgot to say, yeah. What is it? 0.85. Cool. All right. So now we've done that. But let me ask you this. We did a lot of manipulation here, right? We went through and manipulated a lot of these things, but really what did we do? Yeah, if you think about it, we went to all the trouble of making these complicated equations for each of these things, right? And putting the formation enthalpy, but all of the stuff it's made out of just canceled out, didn't it? And would all the stuff it's made out of have to cancel out? Like, if we have 3 carbons over here, and we have 3 carbons over here, then how many carbons will this have been made out of? 3. How many carbons will this have been made out of? 3. So the carbons they're made out of will have to cancel out, right? All of the stuff that makes this kind of messy and confusing cancels out. In the end, what did we really do here? Well, C3H8 is on the left side. It's a reactant. And the only thing we did is we took its delta H not F, and we did what to it? We switched its sign. Good. And then these were on the right. Did we switch their signs? No. But how many carbon dioxides did I have? What did I end up doing to this? How many waters do I have? what did I end up doing to this delta H naught F? What do you think we do to find the delta H of any reaction using its formation enthalpies?
You look at its formation enthalpy for every type of the for every compound in the equation. Let's focus on that and go try to reenact the equation.
That's right. We can use delta H naught Fs to predict the delta H of a reaction. And we can do that by saying this. The delta H of a reaction should be, and I'm going to put not, meaning at standard conditions, but not F, because we're not talking about a formation reaction here. We're talking about any reaction. So the enthalpy change of any reaction should be, what is this symbol? Yeah, I mean, it's a Greek sigma, and sigma is used to mean sum of, which means we're just going to do what with all the numbers underneath it? Add them all up. Good. So we're going to add up all the delta H naught Fs of the products. Did we flip the signs of those ones above? We just did an example. Did the signs change for the delta H naught F of CO2 or H2O? No. The only thing we did is we multiplied them by N, where N is what? The number of moles of each in the reaction. Good. Now, what did we have to do for all the reactants? The only reactant we had in this was C3H8. What did we have to do with its delta H naught F? Yeah, and when we say reverse, mathematically, what did we have to do with that number? Yeah, we had to flip its sign, which you accomplish by multiplying it by -1, or just by subtracting it. Does that make sense? If you subtract a negative, it becomes positive. If you subtract a positive, that makes your number more negative. So we can subtract the sum of what's going to go under this. That's a much better sigma. Sometimes I even get fancy and put like the little serifs on it. So we take the sum of delta H naught F of the products multiplied by the N, where N is the number of moles of each. Then we're going to subtract what's going to go in here. Come on. Very good. Very good. Okay. So this is standard enthalpy of formation. Which you have to look up, right? On this sheet, they should all come from the table I gave you. But if it wasn't on the table I gave you, just Google it. And N is number of moles in the equation. And the balanced chemical equation, how many moles of this thing do you use? Does that make sense? I think we have time to try just one together, which is good because then we will you'll have time to work on your homework and things like that. So yeah, we'll do this one today, and then tomorrow we'll have a work day, and maybe even Thursday we'll have a work day. We'll see how the wind blows us. If we're working well and being productive, then practice. So all we need to know to figure out the delta H of a reaction is the formation enthalpy of everything and the balanced chemical equation. That's it. Does that make sense? So let's look here. We need a delta H naught F for each of these. So C6H6, what's its delta H naught F?
49.
What is it?
49.
49, like just 49?
Yeah, 0.0.
Okay, kilojoules per mole. Cool. 15.5 O2, or 15 over 2 O2. What's that going to be? 0. Good. O2 is just 0 because it's already in its simplest elemental form, so it doesn't need to be made. What about O2, CO2?
-393.5.
-393.5? And H2O. Negative 285.8. Okay. Questions about that? So I'm just putting them all in one place. And so now we can work out the delta H just by doing all the products minus all of the reactants. And remember, it's products, then reactants. And what do we have to do with those numbers? Times them by the n. And I actually didn't mention that in this note here. I mean, I said to do it, but I didn't write it in that little equation, which was silly. I did it below, but not here. That was dumb. So let's go through. What are your products in this? Product. So first we've got CO2. How many of them? So what am I going to write here? 6 times, which is what? Okay, good. And to be honest, I would probably actually write it like this. I would probably say 6 and then just open a bracket, negative 393.5. And then sum means we're doing what with the next one? Adding it. Okay, what is the next one? Next product. Yeah, and how many of them? Cool. So who wants to tell me what I'm going to put here? Who's feeling brave? Someone, oh, there's so many faces I haven't spoken with today. Of course. It would be pretty rude to speak to different parts of people's bodies. I think as a rule, you're encouraged to speak to people's faces, yes. My eyes are up here, Kevin. Was that inappropriate? That was probably inappropriate, and I apologize. That's right. Oh, and look how comfy my shoes are today. So my dog eats the back of the right side of every one of my shoes. So I can't decide if there's something about like the chemistry of my right foot, or more likely if every time I put my shoes in the closet, I like kick off the left, then kick off the right, so the right's closer. But whatever's going on, the right side of the back of the right shoe of all of my pairs of shoes have some degree of being eaten by the dog. Some are mildly nibbled. Some are much more than mildly nibbled, like this pair. And I'm always like, oh, I should throw them out. And I'm like, do I just throw all my shoes out? Like, is this the thing? Like, do I just not get to own shoes? So I keep them, but it's embarrassing. Anyway, okay. What am I doing with water here? Yep. Good. 3. Very good. Okay, and that is all of my products, right? Now what am I doing? Minus. And now for the reactants, what do I got? C6H6. Okay, and how many of those do I have? That's nice. And what am I putting in here? Okay. And I should mention, I'm going to cheat. What am I putting at the end? I'm going to multiply this whole thing by kilojoules per mole, so I haven't cheated and not put my units. Ha! I forgot to put units, but now with a little bit of cheating. Let's see.
But that means the answer is in kilojoules per mole, but like you're still putting in moles in every single one of those things.
Yes. Yeah, that's actually interesting. I'm multiplying by a scalar in this case. So those numbers in front actually aren't united, which we can talk more about that if you want. Let's not confuse us now. I will explain it to you. It has a good faith explanation because the answer to this is going to be in kilojoules per mole. Well, actually, the answer to this is going to be, it depends on how you choose to do it. because we are talking about 1 mole here, I'm going to express this answer in kilojoules per mole. There's also an argument to be made that, yes, I could multiply these all by 6 moles, 3 moles, whatever, and then the final unit is just kilojoules. They're both appropriate ways to approach it. Anyway, somebody punch this into a calculator before that bell rings. Yeah, what do you got? Does that agree with what you had, Alondra?
Oh, no, I was going to ask.
Oh,
we
okay.
do optimize if we did the same thing on the test.
Yes.
But you did it.
Yes. Any questions?
Yes.
Okay, moving on. So that's the basic here. You can use the enthalpies of formation to predict the enthalpy of any reaction. And you don't have to go through all of the Hess's law rigmarole. It boils down to this expression here, because that incorporates the idea of Hess's law into enthalpies of formation. Yes? Because oxygen doesn't have to form into anything because it's already at simplest stage. If you wanted to show it, you would just be saying plus 15/2 times 0. Nothing wrong with showing that. In fact, some people do prefer to show it. I prefer just to leave it out. Anything elemental can just be ignored. And I think recall that any elements have a delta H naught F of 0. That's a great question, by the way. Any other questions? Yep.
The 327 or 379.4.
Yeah.
I think I that. I redid it.
What did you get?
I got 3267.4.
Oh, I love it. We have disagreement. All right. Everyone, what do we get? I don't know. But I do know I love wrong answers. So let's see who's right and who's wrong. Well, not who's right. Who cares who's right? Let's see what's right and what's wrong, because that's the important part.
I disagree. They don't give Nobel Prizes in the field.
You're right. They give it to the right answer, which is why we want the right answer. Well, so we say that, but they don't really. I mean, we understand that one person gets the prize, but that's just for convenience sake. The reality is that that prize is given to a person in his name, but that money is spent in his research lab and goes to hundreds of people to fund their work and is a recognition of the work of hundreds of people. Nobody thinks that one guy figures this stuff out. And note, it's almost always a guy, and he's usually white. Spoiler alert, but nobody thinks that that guy is doing all that work, because he's not. It takes a very broad number of people to make meaningful scientific
I
contributions.
got really different answers.
Okay, well, that's
All right, well, we will listen. What we're not going to do is get stressed out by the algebra. We're going to make sure we can punch this in. Most common mistake, it doesn't actually apply this one, but they forget to put big brackets around everything they're subtracting at the end. That doesn't apply here, so I don't know what would be going on here. Anyway, you guys can figure it out. Do this homework as well. This stuff is agreeably straightforward. All right? Right? It's not rocket science. It's chemistry. But it's do people still watch The Simpsons?
Okay.
Yes.
Now
Damn it, Smithers, this isn't rocket science.